Thank you, Arya. Thank you for the great introduction. Good morning, everyone. As you all know, I am Ahsaas. I'm a senior machine learning engineer at Instacart. And before that, I've spent time at Walmart and Samsung Research as well. Over the last several years, I've had the chance to build recommendation systems that serve like hundreds of millions of requests. And along the way, I've learned something that took me a while to fully appreciate. And that's the gap between ML that works in a research paper and ML that works in production. And it's not about model quality, and it's about something else entirely. And today I want to share with you what that something else is. And before a long wait, let's start with why that matters. So here's the tension I want to set up. In academia, and I say this with deep respect for academic research, we optimize for what's possible. We work with clean data sets. We have unlimited compute for experiments, and success is measured by benchmark numbers. Whereas in production, it's completely different. In production, we optimize for what's reliable under real world constraints, with messy data sets, with strict latency budgets, and with users who don't really care about our AUC scores. They just want the right recommendation right now. And here's the insight that took me years to internalize, which is the gap between the two worlds, which is not about model quality alone, and it is about system syncing. So for this talk, I want to focus on three main things. First, how ML systems actually behave when they meet real users and real data, and not how we hope they behave, but how they actually behave. Secondly, I want to talk about where does the exact academic theory break down. I want to be specific about this because knowing the breaking points helps you design around them. And third, I want to talk about how we architect systems for long-term stability, not just for a successful launch, but for actually months and years to go. But before we get into this, let me paint a picture of why it is so hard in the first place. So this slide may look a little dense, but I'll slowly walk you through what each of these sections mean. Uh, but highly speaking, I'm talking about six challenges that make ML production fundamentally different from research ML. The first one is operational limits. You might have the most sophisticated model in the world, but if it can't serve the predictions in under 100 milliseconds with 4 nines of availability, it's not going to production. I've seen like beautiful transformer architectures that we get inspired by reading a research paper, we implement them, and oftentimes those fancy architectures are replaced by simple gradient boosted trees. This is not because trees were smarter, but because they could meet the SLAs. The strict latency and uptime requirements force simple architectures. That's just the reality. The second challenge is ambiguous ground truth data. Let me ask you a question. If a user clicks a recommendation but doesn't buy it, was that a good recommendation? What if they bought it and then later returned it because they didn't like it after delivery? So the correctness here in like real world systems is very subjective. A click doesn't always mean it's a positive interaction. And silence doesn't always mean it's a negative interaction. And the ground truth in replacement systems is almost always kind of a proxy for what we care about. And proxies can, we all very well know, mislead us, right? So moving to the third challenge, which is often overlooked, which is I call it like product requirements and explainability. Your model doesn't just need to score well offline. It needs to make decisions that very well can be explained to stakeholders. And these stakeholders could be product managers, data scientists, or QA engineers who are looking at these model predictions at 2 a.m. because they're handling an escalation and they don't really understand why the model recommended a strawberry for a banana for an. So explainability has a big role to play when we want to build trust in our ML models and we want higher adoption in real world production setting. Fourth biggest challenge I see is the data, which is non-stationary. We all know the data distribution shifts constantly. There are seasonal changes, there are product launches, there are competitors who are evolving and making their product better. We all know COVID, which was an extreme example, but data drift happens all the time. I often say that yesterday's model is today's stale prediction. A model trained in January may already be stale when you're serving it in March. And the hard part is we may not know it's happening. The fourth biggest challenge, according to me, is the high cardinality decision spaces. At Instacart, We don't have the problem similar to a movie lens problem, where there are like tens of thousands of examples. We deal with like millions of items, and they are spread across thousands of stores all across North America. So the action space is enormous. And when your action space is that large, your data becomes incredibly sparse. Standard models don't converge. They can't converge. They just don't have enough signal per item. And finally, the system complexity and observability. And here's one thing I always feel about powerful models is that they fail wisely. When upstream data breaks, a feature pipeline goes stale, or a policy changes, or an inventory feed lags, our models should not crash. It should not throw an error. It should start producing predictions, which could be slightly worse, which we monitor and then we fix upon. So without proper observability, we won't know all of this is happening. And your metrics will drift down by a percentage of two, and you'll spend weeks looking at the model weights, understanding where the problem is. And that problem could very well be in the upstream dependency. So this is counterintuitive, right? In production, constraints dominate behavior more than architectural choice. And that's the takeaway I want you to have from this slide, and we'll build upon this in the rest of the talk. So let me start with defining what success is and what success is not, right? So let me start with what success is not. First of all, I believe success is not measured by offline accuracy alone. I can't count how many times I've seen model with amazing offline numbers completely fail online. High AUC or offline measures on historical data, it is not always a prediction of how well your model will do in production in real time in the future. Second biggest thing which I feel success is not defined by is the benchmark leadership, right? So we can get state of the art results on movie lens or Amazon reviews, and these results may be great for a paper, but it doesn't mean much when your domain has unique characteristics because your users aren't benchmark users. And the third thing which I feel success is not defined by is the architectural novelty alone. The fancy architectures we often hear about and read about in the papers, it's okay to get excited by that, but it can often lead to more technical debt than business value. So let's take the pivot, right? What does define success? Number one thing, in my opinion, that defines success is consistency over time. Can your system handle the Black Friday traffic? Can your system handle a data pipeline delay? What is there is a sudden shift in user behaviors? So performance stability isn't a nice to have. It's actually a feature. Second thing, predictable failure modes. We all know all systems fail. That's not the question. The question is, how do they fail? When we design good systems, they fail gracefully. When your model encounters an edge case, it should return a reasonable fallback instead of crashing the entire service. The third thing, which I think is success is defined by, is the stakeholder trust. Users rely on our recommendations. Operators trust our monitoring. The product managers, they trust our metrics. And that trust is often earned with consistency. So overall, here's how I think about it, right? A production ML system succeeds when it quietly works every day. And the best compliment is that no one notices it's there. Okay. Now, I want to make all of this a little bit more concrete. So let me introduce you a case study that I think perfectly explains all of these challenges and helps us talk about the next steps. So I choose product substitutions as a case study very deliberately. Let me explain you why. Unlike personalized home recommendations, where a slightly irrelevant suggestion just gets ignored, right? Substitutions happen at a very critical moment, which is very different from a regular recommendation surface. So in a let's think of a user flow for a substitution, right? So user wants an item and they're trying to order it in any marketplace or any e-commerce website, and that item is not available. And the user is already frustrated. They're disappointed that the item they wanted, they can't get it. And now the system has to recover from that situation. Imagine you're a customer, you're ordering organic whole milk for your toddler, but it's out of stock. You're already frustrated. Now the system suggests orange juice. Now, that's not just a lost sale, but that's damaged trust. That customer is now going to think twice before coming to a service again. And this brings me to why substitutions is such a powerful lens for production ML. because the business impact is direct and measurable. Substitutions quality directly affects fulfillment rates, basket size, long term retention. You can literally measure the dollar lost to bad substitutes. But here, what I love about substitutions as a case study overall, that there's no way to hide. With a ranking, a suboptimal ranking can end up in like rank 15. It could be somewhere in the middle of the list. Who's going to complain? But with substitutions, if you suggest a lactose-free milk to someone who isn't lactose intolerant, they notice, and they notice immediately. And this honestly forces us to think about system performance. So let's look at what makes this problem so complex from a system perspective. So we're taking a systems view at this problem now. Uh, so this is what I like to say, that substitutions are like not just a modeling problem, but it's a system problem. As we always spoke about, right? There's a first piece right there, which is customer intent. What does the customer want? And the challenge is to decode all of this from sparse signals. There could be customers who are loyal to a certain brand. There could be customers who have certain dietary restrictions. There are other customers who are very sensitive about price and they only want to go, they want to upgrade in certain categories. And for other categories, they want to be very cautious of what they're spending. Pack sizes, people buy for households, people buy as a single person, right? So they could go for a family pack of something, or they could just for a small packaging. So it all depends on the context and what the customer actually wants. That's first part of the challenge for substitutions. The second piece is the shopper flow. There is a human in the picture, right? So when the order is placed, the human who is a shopper, he or she, they go to a physical store and they start shopping, they look for aisles, and they need to find the substitutes quickly because time is money. And they need confidence that the decision they're making is the right decision, because any hesitation will slow them down. On top of that, there could be shopper and customer chats. The shopper could be guided by the customer in real time based on what kind of substitutes they want or don't want. All of this is added complexity. And the third piece, which is very important, is the inventory realities. Your model might determine the theoretically perfect substitutes, but what if that substitute itself is not on the store? Then the recommendation is completely worthless, right? And this availability changes every time. It's so volatile that it's hard to predict, hard to have an objective function to act around it, but we can still attempt to get to the bottom of it. But the high level principle I want you to take away from this slide is that ML is only a component of a larger decision system. And this is the most important mind shift that happened to me. And I hope like all the ML engineers, practitioners, encounter this and, internalize this, that your model doesn't really exist in isolation. It's a part of the orchestra and you need to play in harmony, right? So your model has to interact with the real-time systems and make sure it's eventually good for the shopper and the customer and the people we care about. So this is how we design a recommendation system like substitutions, and it works in three stages. First is the candidate retrieval, where it's a simple problem. What could potentially replace this item, right? In this stage, we care about high recall. We would rather include too many items than miss the right one because we care about recall, right? And in this stage, we want this stage to be really fast because we're scanning millions of products. We are almost scanning the entire catalog. We have some heuristics on top of it, but we can't afford to be too expensive. We can't afford to be too slow because the search space is so huge. Now, after that comes stage two, which is ranking, which happens after we have our initial candidate set. The decision the ranking layer needs to make is which ones should we show first. So this is where the core ML model is. We're trying to predict what the user will actually accept. High precision is critical here because users only see the top few recommendations and oftentimes they don't scroll as much. So this is where we have all of our complexity about feature engineering, about training data sets, about offline evaluation. All of that is baked into the ranking stage because this stage has direct influence on relevance. Now comes stage three after that, which is re-ranking. And this is where the business logic and the constraints come in. These are the hard guardrails because we want like a peanut product should never be substituted for someone with a peanut allergy. An alcoholic beverage should never be a substitute for a non-alcoholic beverage. The price cannot exceed a certain threshold. The item should be in stock. So all of these are like examples of why we would set up these guardrails on top of a modeling stage, which is a part of like candidate retrieval and ranking. Um, and underneath all of this, again, very important part is something that runs continuously, which is the monitoring and the feedback loops. This could include like tracking latency. It could include detecting drift in our instance data sets. It could include some error rates and a feedback loop that actually takes all of these real world outcomes and feeds back into the system. Again, I'm leaving this slide with an insight, which is like the models are often optimized in isolation, but they have to operate in pipelines. So let's take a case study and a specific example, right? So we train our models on a fixed data set. We tune it. We get great awesome results from it, and we ship it. But in the production, that model sits in the middle of the pipeline. So example, we're talking about a ranking model. So that model sits in the middle of candidate retrieval and re-rank. So the model was trained on a fixed data set. Now it's live in production. And suppose we are making a change in the embeddings that we use for products, and those embeddings are used in the candidates retrieval, right? So when the model is running in production, there are instances where the output distribution of the candidate retrieval might change drastically. It could have a different set of candidates. It could have a different number of candidates. It could have a different feature distribution scores. So all of that makes the model, which was correct and it was shippable, slowly degrade in value because that model was trained on an entirely different data set when we initially shipped it. So all of these things make sometimes the model and the system very brittle because there is clearly a distribution shift between the training time and the inference time. And oftentimes all of these mismatches go unnoticed. So that's why we need the monitoring and the feedback loops to be able to make sure when we first ship the model versus when the model is running in real time, day after day, the performance of the model is at par. So that's one insight I would like as a takeaway from this slide is that the errors may not be in the model because they are often tuned in isolations, but most of the errors can happen in the boundaries of these blocks, which constitute the bigger system. Moving to the next slide, I want to talk about some early design constraints that if you ignore them in the start, they will come back to haunt you. So the first one, which is very common for anyone working in recommendations, is the cold start. Why this is a problem? Because we launch new products every day, we expand to new cities regularly. How do you make good recommendations with items with zero interaction? And we all know about collaborative filtering, but that's useless here. And we need content-based fallbacks. We need smart initialization techniques. And this has to be designed and baked in the system from the start. Second constraint is sparse and delayed feedback. Think about the signal to noise ratio here, right? A product might be shown thousands of times, but it could only be selected a dozen of times. So if you show a product as a recommendation in your system thousands of times, there's no guarantee the customers are going to like it. And they might have very sparse signal on it. So we have to deal with such cases where the impression rate is really huge, but the actual selection or engagement is really low. Second, another issue is that feedback that comes from the customer could be really delayed because they could give a poor rating or a good rating on an interaction or on a recommendation weeks later. So it becomes challenging how you parse all of this information to ensure you get clean data sets and you have clean evaluation. Third constraint is long tail dominance. In grocery, it's a known fact that almost 80% of our revenue comes from 5 or 10% of the head products. But the remaining 80% of the catalog is the niche items with very few interactions. So if our models only optimize for the head items, you're leaving money on the table. You're frustrating the customers who want specialty niche products. And that's one of the biggest challenges I have seen personally with my work in Instacart as well. Fourth constraint I want to talk about is real-time availability. So the perfect recommendation that we have, as I mentioned earlier also, it's worthless if the recommendation itself is out of stock. And we know the inventory at these grocery stores, they change very dynamically. And they can also change between the time you generate the recommendation and the time the shopper actually reaches that aisle. So I want to be like really direct about something here, right? I've seen teams design these systems that ignore all of these constraints, and I've been doing that for a long time early in my career, thinking that they can be addressed later. But the reality is, it's very hard to course correct after you have built your systems without keeping these constraints in mind, right? So now let me move to the next slide, which is again a few things that we do earlier on when we're building our recommendation systems. It could be a V1, right? So the the first of all, we think about why not heuristics? Why can't we make rules that can solve all of these issues and still uh, take us on the happy path? And these rules could be like either like matching similarity or matching something with the catalog, or just hard coded rules like if something is organic, replace with organic. It can be clear, it can be simple, it can be explainable, and we can write like a huge if else statement for this. But I want to talk about why these rules break, right? Let me go through step by step again. Most of you would be familiar if you are real world ML practitioners that these are the reasons we can't scale the rules and we need something which is embedded in machine learning. I won't spend too much time on this slide, but just a high level gist of what I'm trying to explain why these rules actually break at scale. Number one is the context in the personalization, because these personalization attributes are not universal. What one user would accept for an item at that moment, it could completely be unacceptable by the another. Second, we have a lot of assumptions baked into when we make these rules, and these assumptions often break, right? Like uh, because you're not actually encoding the data, like what the data is telling you. You're not learning from the data. You're just building assumptions, and it can often go stale, or it can often go too complex that you can't really make them scalable, and it can't solve the issues down the road. Right? Talking about scalability, we also know our catalog grows, our inventory, like there are churns, and there are a number of rules and exceptions that can explode. So you really can't write rules about every product, every category, every user. Um, and they also don't scale well with time. And they are static rules that don't really solve the problem in the long run. So again, most of us are probably aware of this, but I just want to put it here for completeness that rules alone are not the way to solve all of the challenges I've spoken in the past. So now let's talk about some core design trade-offs. And this slide is it's really important, right? I'm talk about three trade-offs that you would face in any production ML, and how you determine them determines the long-term health of your system. So just a quick time check. I think we are at almost 30 minutes. I'll try to speed up, and if there are certain slides I would like to skim, feel free to go back and review them, and you can reach out to me for any questions later on. So yeah, I'm talking about the three design trade-offs here. The first trade-off is simplicity versus complexity. So there is always often a pressure to use like more complex models. Transformers are the state of the art. Let's use transformers. This new architecture got great results in that paper. Let's go use that. But as we briefly spoke about this in this presentation, that the complexity has costs. It makes debugging a nightmare. There are more failure modes. It makes our iterations slower. So the goal isn't really simply we're not trying to be simple just for the sake of it, right? The goal should be earn complexity. We should only add complexity when you have proven that the simpler approaches are not sufficient. Trade-off number two, generalization versus personalization. So oftentimes when you're building these ML systems, personalization feels like the obvious answer, given each user exactly what they want. What could go wrong with that, right? But I believe a lot can go wrong if there is too aggressive personalization, and it can create problems for us. One biggest problem is the overfitting on sparse signals, and the silent regressions that can be caused by these filter bubbles, where the global metrics improve, but the specific user segments suffer. So my advice is, and what I've seen working in production is start with strong generalized baselines and then layer on the personalization incrementally. Moving to the third trade-off, offline metrics versus the real world outcomes. So this could be the most dangerous trap. We often, when we build these models, we track offline metrics such as AUC, NDCG, recall, the standard ML suite of metrics, and we improve them. We get excited, and then we launch the model, and at times, nothing really happens. The business metrics don't move, the customer engagement doesn't skyrocket, and we often ask questions to ourselves like, did that happen? And the answer is really brutal, right? Because our offline metrics are proxies, and the proxies can often mislead. And the goal is to build trustworthy proxies, the offline metrics that actually correlate to what you care about offline. Now, this is again a high level of the three trade-offs. Let's go deep into each one of them, and let's be precise with what my recommendations are and what I'm trying to say here. So yeah, first one, simplicity versus complexity. So after having to work in like ML engineering for a long time now, this is kind of a goal I've set for myself, that the goal of ML engineering and goal of a good ML engineer is to control the complexity and not to create it, right? So why do simple systems always win in production? Let's go step by step. One, they're easy to debug. When something goes wrong at 2 a.m. and it will go wrong at 2 a.m., can you trace the decision logic? With a gradient boosted trees, with an XGBoost, we can actually look at the feature importances. We can examine the individual decision paths, and we can examine and understand why a specific prediction was made. But with like a multi-layer transformer architecture, it's much harder. Second, they're easy to monitor. Simple systems have very few silent failure modes. You can build dashboards that actually tell you when the things are broken because you understand what broken looks like. Third, they fail in predictable ways. When a linear model encounters unusual input, it gives an unusual but a bounded output. But when a deep neural network encounters unusual input, it might give confidently wrong predictions. It doesn't know what it doesn't know, right? Fourth, they allow fast iteration. When your baseline is stable and understandable, you can test and do A/B test quick ideas really quickly. You know what you're comparing against. You can isolate the impact of these changes. Let me share something I witnessed. Right, I saw a team replace like a big, giant deep learning model with XGBoost. Same features, same data, but we saw business metrics improved. Not because the trees were smarter again, but because the simple models have fewer catastrophic failures, and you know what you're building, they're easy to explain, they're easy to test, and they're easy to iterate. Next up, personalization versus generalization, right? We know personalization is very seductive, right? It gives users what they want. What could possibly go wrong with that? Let me show you what. Number one, overfitting to narrow signals, right? So user clicked on something once. Now the model thinks they love that category. They want to see more of it. They click because it's there. The model thinks it's right, right? So you see what I'm hinting towards. When we push the throttle too much on aggressive on personalization, we often start capturing these narrow signals that don't mean as much as we think they mean. And this creates filter bubbles. Users only see variants of what you have already seen, right? So you sort of like go in that feedback loop where you diminish the discovery and you are full in the exploit mode. And the recommendations often have very little explorations that our customers would actually love. Third is we spoke about the feedback loop. And the last is the silent regression, right? So your metrics look great. The average satisfaction could be up. The dashboards could be green, but there could be these cohorts of users that would not still be happy. It could be like either new users or it could be users from a certain demographics who have zero personalization signals, and they could be having a terrible experience, but we won't see this in aggregate numbers. So due to all of this, I believe we should take a step-by-step approach, right? Which is safe for production, it's safe for the business, and we would know what we are building towards, right? So step one would be to have strong generalized baseline. It could be based on popularity. It could be based on trending in your area. It could be based on certain segment or certain clustering-based models. So we want to make sure something that works for everyone before adding personalization too aggressively. Step two would be when you introduce personalization as a re-ranking step on top. You could use certain user history features to adjust the ranking, but the baseline ensures that we have reasonable coverage and a lower bound of relevance throughout. The step three could be to keep the guardrails separate from ML scores. Right. So the business rules we spoke about availability, about dietary constraints, about price limits, these should never be overridden by personalization signals, as these are super important to uplift and continue the high trust the customers would have in our system. So let's talk about the last constraint, which is the offline and the real world outcomes. And this might be the most important to get one right. So firstly, let's talk about the offline trap. Uh, we have discussed this in one of the initial slides that the high offline metrics, it could be AUC or NDCG, it does not always mean more conversions. Why not? There could be a few reasons to it, right? So we could be overfitting. Number one reason would be that we are overfitting on like historical biases in our training data, which means we are great at predicting what happened, but it will, but not what will happen, right? We are predicting what has already happened. So we might be ignoring some downstream system effects here. So your model is great, but it recommends items that are always out of stock. So gate predictions, terrible outcomes. We spoke about some of the inventory challenges before. It shows up again here. So offline data sets and offline evaluation doesn't really tell us the things that can go wrong in production, where you have certain nuances about inventory and certain business rules that come into picture to make the final recommendations to the customer. The second bullet I want to touch here is the intent and the proxies. So what really are we trying to optimize? We all know we are trying to optimize user satisfaction, but we can't really measure user satisfaction directly. So we definitely need proxies. We need clicks, we need purchases or dwell time, right? And the key is that this is critical. Like the designing the proxies that actually correlate to the satisfaction and validating that correlation is the most important investment I think any ML engineer can do. And I've seen like multiple experiments, succeeding in my journey, that you could do the heavy lifting of defining what those proxies are, defining what the offline suite looks like, and it's a one-time effort, right? Once you are really confident on that this is my suite, it just makes your iterations super easy because now you can trust the numbers you see in front of you. Instead of just doing an A/B test for any new model update you do, you could run like serious ablations and hundreds and hundreds of model iterations offline and save the effort energy it takes to do an A/B test because now you can trust your offline metrics and they are correlated with the business metrics you care about. So the trust and the iterations are the two takeaways in my learnings, and I would really highly recommend everyone to focus on building these offline metrics that actually track like end business value. So let's talk about how do we operate over time. Again, I'm keeping a time check. I know we have 20 minutes left. I'll like just speed up the end part of my presentation here. But we are I would say like these are some of the challenges we have already spoken about briefly in this presentation, about the data drift, about like new items being added, being able to do cold start, and these seasonalities and spikes during holidays. So the system should evolve and ensure it handles all of these scenarios correctly to be a successful production system. Um, Again, quickly about what we should be monitoring and the feedback loops. I think we've also briefly discussed about this. The distribution of the data that's coming to each component of the system matters, and we need to have detectors that alert us if there is a serious shift in the distributions. And output behavior, right? Every model's output has a certain distribution, and we need to keep an eye at it, right? There could be some downstream or some upstream issues, such as some of the feature processing, some of the data logging could go wrong that can change the ML score distributions by a lot. And that may not show up in the product metrics as easily as it may show up in your sensitive ML monitoring and evaluation. So I would highly recommend folks set up these monitors, set up these alarms to like just capture anything egregious earlier on before it eventually impacts the final customers and customer trust. So, so far, whatever we spoke about, right? So everything we've discussed applies to um, many models and many systems beyond product substitutions. It could be like some recommendation systems at Netflix, Spotify, anywhere we have like these high cardinality challenges. Even search and ranking, like the same trade-offs between personalization, generalization, complexity, and simplicity apply to any search and ranking system. And the feedback loop we talk about can be a big part of consideration when building ad systems or when building social media feeds. So the playbook we went over about like the high cardinality, the multi-signal feedback, and the trust evaluation are much beyond product substitutions, and where we use the product substitutions as just one case study. I'll just end by sharing where I see production ML systems going. First, we spoke a lot about reliability, and reliability will continue to be a first class goal, in my opinion, and not an afterthought. It's not something that you think after shipping, but it should be the primary objective and it should be baked into the systems from the get go. Second, in my opinion, I'm a big believer of hybrid intelligence, where we are seeing a rise of Gen AI, and we are seeing already like a lot of generative recommendation systems being built. But I'm keeping my eyes open to how these generative ML systems would interact with the traditional ML systems and go hand in hand, and what are the cases we can solve with generation of recommendations versus predicting recommendations from our catalog. And the third thing, which I believe will always be important, is operability. Right, as systems become more complex, the black boxes become liabilities, and we are seeing a lot of push towards explanations and being able to understand why a model is making that prediction, so that we're not operating in black boxes, and we know what the model outputs are, and we can build trust based on that. So this is where I would end, and I'll just add a quote at the end of my presentation, which I often use in my interactions with peers. Is like the production ML, according to me, it's not about being clever once. It's about being correct every day under change and at scale. And I will leave you with this one insight. And we have like 15 minutes left, and at the end we can open for questions.
Great. Thank you, Ahsaas, for this wonderful session. There were so many useful insights. But now let's open up the floor for questions, any insights. Would anyone like to share anything? Please feel free to open up your mics. I'll just wait for a minute if anyone would like to speak up. If not, there are two questions that are posted on the Q&A channel, so I'll just move to those. But yeah, just giving a minute here.
Hi, Ahsaas, what do you think about the agentic AI systems that are currently being uh, totally kind of uh, involved in your day-to-day use, like the Claude bot or the recently renamed, I think so. It was to Moho bot or something like that. So with that, the production systems are currently moving, and so what are your thoughts towards that?
Yes. Yeah, good question. I think I'm keeping a close eye at where how the agentic AI space is evolving. To be honest, we have used AI in like some of our recent inventions, but it's not been able to. We've not done like real production serving with like accessing with our catalog and with access to millions of items. We have done like some offline evaluations, some qualitative checks, and even like some real-time interventions in the whole shopper customer flow. But still, we are trying to understand how it can access this huge catalog and generate recommendations from this. Like, how can we give such a huge context with uh, catalog and the metadata and the user preferences all baked into the context for it to generate recommendation from it. It's still in exploration, But I think we're keeping a close eye at it.
Cool, thanks.
Yeah, Ruchira, go ahead, please.
Yes, thanks, Arya. Thanks for the great talk, Ahsaas. I'm in academics to get this very deep approach can go wrong and what can go right in industry settings. One thing I require is generative AI. Like when you have evaluations or you've done around some testing. So, do you feel that for your use case or whatever you're planning to use a Gen AI model for, do you think the existing evaluation benchmarks are they useful? Do you feel like you always have to end up crafting your own evals?
Yeah, I think with the agentic recommendations, definitely we need to craft our own evals. What I've seen work well for my use case, and my experience may be limited here, and there are other folks who are pushing AI at Instacart much more thoroughly than me. But we have like closely looked at the older evaluations we used to do, maybe human evaluation or qualitative evaluation, right? And we are taking that as a baseline, as a reference, and then building AI-based evaluation trying to mimic how a human evaluator would rank it. So you have heard about AIQA, right? So AI-based qualitative evals, right? So we use the human evaluators and as a reference point, and we try to mimic how good a job an AI-based evals can do, which a dedicated domain-specific evaluators would do. So based on the match rate of this is our AI-based evaluation of the same data set, and this is the human evaluation. We try to compare them against each other. And then after a point, we see there is a high correlation between a human evaluator versus an AI-based evaluation. That's what flips the trick for us, right? Like that flips the switch that, hey, like now we can trust this AI evaluators because we have done human evaluation for so long. And now this prompt and this model and this context can do an equal or better job. And that's like a one-time hard work, right? Once that is done, it makes our iterations much more faster.
Okay, that makes sense. And just one short follow-up on this. Like if you were kind of trying to decide between different models used, so suppose there's a use case where you'd like to use one of the Gen AI LLMs, like, it could be Claude, GPT, or whatever. So what kind of factors would play into you choosing one over the other? Is it your own crafted evals? Is it you're going to run some benchmarks? Or does it completely depend on something like latency or other considerations?
Yeah, I think latency and like how well the system performs end to end with that LLM in the picture, right? So again, according to me, like ML AI, like we have to think from systems perspective. Like it can work well in isolation. There could be one model which could be killing the benchmark, but when you plug that into the whole shopper customer flow, if that LLM is not able to make decisions that can unblock a shopper who is trying to make replacements at ShopRite sitting in an aisle, that LLM will not be a hit for the business. So like a model that can make like twice as fast decisions with a little bit more certainty and maybe a little bit more explainability so that you can build that trust with the customer who is sitting at home. That actually matters equally as much as the offline evals. So I would say there's a suite of things. There is like how well it can be plugged into a system, how well your customers and shoppers respond to it, keeping other facets like explainability and latency in mind. And of course, the evaluations are very critical because without that, you can't really ship. So I would say there's a combination of multiple things. Uh, Again, the high level idea is like what works in offline setting may not be the best judge of what would be a shippable candidate.
Cool. Thanks for that. Again, thanks for taking time for the talk as well.
Thank you for the questions.
Yep. I had another quick one with respect to like how do you like there are algorithms for coming up with the recommendations based on the seasonality as well as the month wise or the festivals that each month offers, or like there is the data drift that you have to keep check of and like update your models with respect to that. So like do you also think that uh, the a use of reinforcement learning for the rewards, like we do it in LLMs? Will that kind of work in this in these recommendation systems, or like do you guys have experimented with that, or what are your thoughts there?
Yeah, again, a good question. I personally don't have experience with like RL based recommendations, so I may not be the right person to answer. But what we have, the way we have addressed seasonality and these data drifts is having a continuous charter at which we train our models. So like we often see like user predictions and user behavior could change either quarter by quarter or half by half or year by year. So what we have done at our systems is to have a continuous charter of model retraining, and you need to know when to retrain the model. So the step one is always about observations. So we need to have this continuous monitoring to really tell us like which of your 100 models are now not performing as good as when we first shipped them. And then that like basically becomes a trigger point on going and checking like, is it the right time to retrain the model? Was there a change in the UI and the UX that, hey, initially the customer was seeing 10 recommendations, but now due to some UX changes, on average, they only see 3 recommendations in one screen. So if product makes that UX changes, right? So now that will have a downstream impact on your model performance because your model was trained on like 10 recommendations in one view, but now it has 3 recommendations. So this could be one drift, as you're talking about. But personally, like I have paid more attention to monitoring there is a drift and having certain alerting that indicates that the model is getting stale or there was some spike that happened because of certain ship that could be outside ML, and then going ahead and retaining the models. But to your point,
Thank you.
All right. If anyone else have any questions, please feel free to
Yeah,
raise
hi.
your hand.
Yeah,
Yes.
hi,
Yes.
Ahsaas. This is Shukneet. First of all, thanks for the session. I mean, that was really insightful, and the examples were really uh, relative. I have one question. I think you gave a similar example to this. Like, how do you measure the quality of the output when there is no ground truth? Right? We are generating too much of data. Sometimes you do not have, like you said, right? You have one product that shows up 1,000 times, but the buyout is only 12 for that. So how do you measure those kind of that these things shouldn't come up, or if it's coming, it should have uh, uh, some actual, I think, why that particular product it's showing up. So is there a way we can have some framework or benchmark?
yeah, sorry, Shubhneet, I lost you in the middle. I was having some audio issues. Can you quickly repeat your question, please?
Yeah. So I'm saying you gave an example, right? Where like one product like shows up is showing to the customer 1,000 times, but it is actually picked up like a dozen of
Yeah.
times. So
Yeah.
just wanted to see, like, if you do not have some ground truth or ways to validate the output, why this is showing up. So do you have a framework which we can leverage based on your learnings?
Yeah, so I think what you're talking about the sparseness in the user feedback, right? Like there could be a product which believe is a very popular product because it gets a lot of impressions, but it's not likable as a replacement substitute for a certain category. So it could be it is a good product to show in search and recommendations, but not good of a replacement. I think that's what I understood from your question, and this problem happens a lot. Talking about frameworks, I don't believe there is a specific framework to like handle it. I think it organically flows into our data pipelines. So like as long as your model has the right kind of features, right? So the feature for fixing this problem would not be the count of impressions or the rate of impressions, but the rate of approval or for the rate of customer picking that product as a replacement. So as long as the system has these representative features or embeddings that can look beyond the raw counts and look beyond the popularity signal and truly get to the point where we can actually predict the user selectivity and the user engagement. I think that organically solves for itself. So we don't need specific frameworks for it. We just need to understand this nuance and make sure our data logs it, captures it, and then we make sure our model is powerful enough and it has the right features to be able to distinguish between just a popular product versus a product that is selected by the users as good replacements.
Okay, this helps.
I
Yeah,
hope that
thanks.
answers.
Yeah, thanks.
Any more questions?
All right. I'll just read out the Q&A questions that were shared. The first one, I think you've kind of answered this with Ruchira's question, but basically the question asks, I agree that offline accuracy and benchmark leadership are weak signals of success. What early signals do you trust the most before you deploy a system fully?
Yeah, so there are a few ways to handle it. I think one which I addressed in the deck is not all offline metrics are sort of like useless or are not that great. What I'm trying to focus is we need to focus more on building these offline metrics for our domain, for our systems that we can then trust and be confident before shipping an experiment. So like one example I could take is like you could build like a suite of 20 different metrics, right? And see your offline evaluations for a new model for those 20 metrics, and then ship a live experiment, and then try use that live experiment data and the offline data to build certain correlations and understanding going forward which out of these 20 metrics can you really trust and by what multiplier. So like doing your exhaustion of these metrics offline and trying to get to a point of like how can you slice and cut the data so that your offline numbers are actually predictive of your customer value, which you would get in an A/B test. So like doing this series of experimentations and then building confidence in your evaluation metric is the proposal I was going ahead with. That would then blast your iteration velocity because you now are looking at the numbers that you can trust and you have precedence by running live experiments that these numbers actually move the needle. So that would be my takeaway.
Yeah, that makes sense. And the second question is, so how do you protect, I think, product discovery and encourage exploration of products when personalization pressure is high? That's the second question.
Yeah, I think there is a good term, right, in the industry, like exploit and explore. So any system should have a component of both. And the way you could do this with like either, we spoke about certain features, right? So we not only have like user level sparse features, but having like features at different hierarchies, like product level features, retailer level features, or category level features. So like breaking down your features or your input data sources across these different hierarchies would ensure your model is not just personalizing, but it's also doing the exploitation and not like it's also doing the exploration with the exploitation. So I think looking at like these different category of features would be a good start, and just thinking your solutions from different facets like explore and exploit.
Yeah, totally. All right, I think our time is up right now, so let's not waste a lot of time. Let's bring the session to an end. First of all, thank you so much, Ahsaas, for joining us today and for sharing your insights on recommendation systems. The case study that you did was wonderful. There were lots of takeaways, especially for ML engineers, people who are starting out with productionizing ML systems. To the audience, if you have any more questions or would like to revisit any part of the talk, feel free to reach out in the community channels on Discord, and we'll also share the details about the recording there. Thank you so much to everyone who joined today. Your participation and your questions are highly valued. All right, thank you so much and have a great day.
Thank you.